I'm Franz Fuchs from the University of Cambridge. We at the University of Cambridge, together with our partners, are working on a research project called CHERI. CHERI stands for Capability Hardware Enhanced RISC Instructions. The fundamental feature of CHERI is a capability. A capability extends integer pointers as you know them from your C programming language. A capability adds, on top of that integer pointer, it adds metadata. These metadata are permissions and bounds information. So a capability does not only describe a memory region, it also authorizes access to it. On the right-hand side of the slide, you can see a memory region, you can see two bounds, and you can see the pointer address, which can freely move between those bounds. And only if the pointer address is within those bounds, then the capability does allow the access, otherwise it doesn't. Obviously, you can also manipulate capabilities, but this needs to be in a guarded way, which means that we ensure both provenance validity and monotonicity. The last final and very important piece of capability is the validity tag. The validity tag allows us to distinguish between data and a capability. So we can distinguish between data and an actual pointer that then points to a function, for example. Together with our partners, we have brought up an entire CHERI RISC-V open source stack. This includes the documentation, then the specification in the SAIL model, so we can then do formal verification on that. We also have simulators, most importantly QEMU. We have ported an entire Clang LLVM toolchain, so we can just compile C code, and then we get a CHERI binary. We have multiple operating systems. Most importantly, we have CHERI BSD, which is based on FreeBSD. Today, I want to show you one of our hardware implementations, also put a photo up there for everyone who cannot see it. On this Stratix 10 board, there's a superscalar out of order core, which we call CHERI Tuber. So let's actually straight jump to this. So this is a full operating system running. So this is CHERI BSD and me as a user on it. And it's just fully functional. So I can just use ls or whatever. So let's see what we actually do. So you see, this is CHERI BSD, and this is one of our Jenkins builds. Brilliant. So what is actually running on this system? So let's run procstat, and we'll see that we have we have multiple processes running. Some of them are kernel, some of them are for the user. And we see that here we have the ABI. And the ABI says ELF64C. So this is a 64-bit ELF, or 64-bit pointers. And the C stands for capability. So every process on this CHERI BSD is running with capabilities, apart from the kernel processes or the initial kernel processes. But this is a pure capability CHERI BSD. Brilliant. Now let's actually look into let's actually look a bit into how we can use capabilities. So let's look at a quite simple code. In this simple code, we print the size of a pointer, and we print the size of an address. On a normal system, these two should be the same thing. So let's execute the baseline program. This has already been compiled. And what we see, the size of the pointer is the size of the address, 8 bytes. Nothing too fancy. But now we run the CHERI program. And we see that the size of the pointer is actually 16 bytes. And the top 8 bytes are the metadata. Very cool. So let's see how we can mitigate an actual attack with that. So what we are going to do is look into a typical buffer overflow stack attack. So let's look into the source code. So what we have in the main program is that we have two buffers, upper and lower. They're both 16 bytes in size, and we then print them to see how they are laid out, and we assert that they are laid out exactly below or above each other in memory. What the program then does is it writes, in this line here, it writes the character A to the buffer, and then it prints at the buffer upper at the index 0, and then it prints it in the line afterwards. The next important thing is an invocation of the write buff function. Write buff writes to a buffer at the index x. So what we do is that we write to the buffer lower, but we write at it at the size of lower. The size of lower is going to be 16, which means that we write at index 16. This is going to be a 1 byte overflow into upper. Then we again print it, and then we end the program. So why don't we actually run this program? So we run the baseline program. We see that the two buffers are aligned right next to each other. The difference is exactly 10, so hex 10, 16 bytes. And we see that we have a successful buffer overflow here, because a upper 0 has become B. So then we run the same thing for CHERI. And we see that, yes, the layout is slightly different, but that's quite to be expected. They're still laid out 16 bytes after each other. We can write to upper 0, but when we then do a buffer overflow, we see that we get an in-address space security exception. And that's exactly what CHERI does. We try to access a capability out of bounds. It's not allowed. And then the operating system handles the hardware exception for us. I do think, for time reasons, I'm going to end the demonstration here to allow for a few more questions. Thank you so very much.
There's one question in the back. Let me just come.
Hi, thank you for the presentation. Where can we find you if you want to see the demo again? Do you have a booth here where you're presenting this?
We'd like to have a booth. Unfortunately, we couldn't arrange so. What you can do is to download this. This is obviously all open source, so you can download our entire workflow, make it work. We have loads of documentation on this, and we are more than happy to support you to get started.
So, no more presentation questions. Sorry. So thank you, and this concludes our demos. Thank you, everybody. Thanks, Centaurus, for sponsoring the slot, and see you around.